Hello, everybody, and welcome to the lecture for Tuesday of week 12. So today we're going to talk about sums of two squares and the method of descent. Okay, so the basic question today is which integers n can be written as sums of two squares? So when can I write an integer n as a squared plus b squared, where a and b are both integers too? So for example, I can write 10 is 3 squared plus 1, and that 1 is really 1 squared. So that's a sum of two squares. But if you sort of just start writing down all the possibilities, you'll see there's no way to get 19 as a sum of two squares. So the answer is sometimes yes and sometimes no. And we'd like to understand, well, one, when is the answer yes? And then two, sort of if I have an integer where I know the answer is yes, how do I actually write it as a sum of two squares? And this will build on some things we did with quadratic reciprocity. It'll also build on things we looked at with the Gaussian integers, going back to the week where we talked about quadratic integers. Okay, and right, so we're going to give a complete answer. And this complete answer, and another way to think about it will actually be sort of, it's essentially equivalent to a unique factorization theorem in the Gaussian integers, z brackets I. Okay, so it connects to lots of things we've thought about before. Let me make a couple of simple observations about this problem. The first is if you have an integer that is written as a squared plus b squared, well, in particular, it's at least 0. And that's just because a squared and b squared are both greater than or equal to 0. And if you square any real number, you get a non-negative real number. So this is sort of simple. So we should just look at positive integers. And then another nice observation is that if I add together two squares, well, I'm going to get something that's congruent to 0, 1, or 2 mod 4, just because a squared and b squared are both congruent to 0 or 1 mod 4. So only squares mod 4, if you just sort of run through and try everything, you'll see the only squares mod 4 are 0 and 1. And so a squared and b squared are sort of both congruent to 0 or 1 mod 4. If you add together sort of 0 and 1 mod 4, you either get 0, 1, or 2. So n is going to be 0, 1, or 2 mod 4. So already sort of we rule out some possibilities for which things can be written as sums of two squares. A more interesting observation is that I can sort of break this problem apart because if I have, so this is stated as a theorem, and I'll explain why it's true in a second, but if I have m and n, and they're each a sum of two squares, then the product m times n is a sum of two squares. And so this is an easy consequence, actually, of the norm. So let me write down. So if m is equal to a squared plus b squared, and n is equal to c squared plus d squared. Well, another way we can write this equation, m is equal to a squared plus b squared, is to say that m is the norm of the Gaussian integer a plus bi. So that's just sort of, and then n is the norm of the Gaussian integer a or c plus di. So remember the norm of x plus yi is x squared plus y squared, which you can also think of as being x plus yi times x minus yi. So you can sort of think of this as coming from just multiplying a complex number by its complex conjugate. We saw this is something we talked about like on the assignment where we were working with quadratic integers. So we saw there was something like this. We saw there was something like this norm for any sort of z square root of whatever. And then we also used this again last week when we were talking about like FP brackets I. So this is something we've used quite a few times now. Good, so m is sort of the norm of this Gaussian integer and n is the norm of this Gaussian integer. But then m times n is just the product of the norms. And so the key thing about the norm that we proved way back on this first assignment where we introduced it, or you can sort of deduce it pretty quickly from thinking about it as sort of being a number times its complex conjugate, is that the norm of a product is the product of the norms. So this is the norm of A plus BI times C plus DI. Which, if I expand that out, well, I get AC minus BD plus, so when I sort of expand with the multiplication inside of A plus BI times C plus DI, I get AC minus BD plus AD plus BC times I. Okay, and so this is AC minus BD squared plus AD plus BC squared. Okay. So of course you could just sort of check that this formula holds. Sort of m is a squared plus b squared and n is c squared plus t squared. Then m times n is AC minus BD squared plus AD plus BC squared. You could just expand that out and check that that really was the case. But sort of this is a nice way to see why this holds. It's just coming from multiplicativity of the norm on Gaussian integers. Okay, but in particular, sort of if m is a sum of two squares, then m times n is also a sum of two squares. So both of these are integers because a and b, c, and d were all integers. Okay, so this is very powerful. And so, for example, just to illustrate it, like 5 is 2 squared plus 1 squared. 13 is 3 squared plus 2 squared. So if we want to express 65 as a sum of two squares, well, 65 is 5 times 13. So we can just multiply 2 plus I times 3 plus 2I to express 65 as the norm of, if you expand that out, you'll get 4 plus 7I, which means 65 is 4 squared plus 7 squared. Indeed, 16 plus 49 does give you 65. So this sort of gives you a quick way, sort of if you sort of, for example, if you know the prime factors of a number are sums of squares, then you can write the number as a sum of squares. That's quite nice, and it also suggests that sort of using prime factorization, a good first question to ask is actually just which prime numbers are sums of two squares. And so that's what we're going to focus on answering today. And then on Thursday, we'll come back and answer it sort of for general n. So which primes are the sums of two squares? And let me just recall that in the very first week, our very first in-person class, so on the Thursday of week 1, you noticed, you worked on this exercise 3, and if you worked on that, you noticed that for p less than 100 prime, then p was equal to a squared plus b squared. Well, p equals 2 works because 2 is 1 squared plus 1 squared. And then, so once you move on to odd primes, you saw that sort of you could write it as a sum of two squares exactly when p was congruent to 1 mod 4, but you couldn't when p was congruent to 3 mod 4. So this is consistent also with the examples I've done so far, like 5 and 13 were both congruent to 1 mod 4, so that's why I had them in this example. Whereas somewhere earlier, I wrote, so 10 is 5 times 2, and so sort of the prime factors here were both congruent to 1 mod 4 or 2. And then 19, the way I said there was no way to get 19, and 19 is a prime is congruent to 3 mod 4. So that's sort of a quick way to check sort of if you know this fact without just sort of trying all the possibilities. Okay, so this sort of observation that you made in the first week, that for p less than 100, a prime is prime p less than 100 is a sum of two squares if and only if it's congruent to 1 mod 4. So that's consistent with all the examples we've done so far today. And in fact, this really gives a condition for prime to be a sum of two squares. So the theorem says if p is a prime, then p is a sum of two squares if and only if, well, either p is 2, so p is 2, or if p is an odd prime, then it has to be congruent to 1 mod 4. Okay, so one part of this statement is very easy. So the fact that it's necessary that sort of for p to be a squared plus b squared, that you have to have p congruent to 1 mod 4 or p equals 2 just comes from this simple observation we made at the start. I mean, here, if you have p, and if n is a prime, well, it's going to be congruent to 0, 1, or 2. if it's not 2, like if the prime is not 2, then it can't be congruent to 2 mod 4 because then it would be divisible by 2. And so it can't be 0. So if it's an odd prime, then it's the only thing left for it is to be 1 mod 4. So that's sort of why if your sum of a prime is the sum of 2 squares, then it's not 2, then it's 1 mod 4. So the hard part then of this statement is to check that if this congruence is satisfied, so if P is congruent to 1 mod 4, then in fact, so if P is congruent to 1 mod 4, then in fact you can sort of find A and B such that P is equal to A squared plus B squared. And so we're going to show this holds actually by sort of explaining not just why it holds, but really we'll explain it by giving you an algorithm that you can use to find A and B. And then on the worksheet on Tuesday, we'll sort of go through running that algorithm. And then on Thursday, we'll see a different way to think about this. Okay, so how does that algorithm work? Well, there are really 2 steps. Step 1, you're just gonna, instead of, you're sort of solve an easier problem. So instead of finding A and B such that P is equal to A squared plus B squared, you're gonna just find A and B such that some multiple of P, so M times P, is equal to A squared plus B squared. Or in other words, A squared plus B squared is congruent to 0 mod P, but this M doesn't have to be 1. So first we're going to find a solution to this sort of simpler equation. And then we're going to do sort of this method of infinite descent, which means we're going to start with a solution like this. And then we're going to play around with these A and B. We're going to modify them a little bit to end up with a new solution, sort of to end up with a new thing, new numbers A prime and B prime, such that the sum of those 2 squares, A prime squared and B prime squared, is also a multiple of P, but now you get a smaller multiple. So you get some M prime that's less than M. And we'll just do that and we'll sort of repeat until we repeat the second descent step until you sort of end up with this multiple just being 1. And that gives you sort of your way to express P as a sum of 2 squares. Okay, so let's talk about how you do this first part. How do you find A, B such that A squared plus B squared is equal to NP? Well, first, let me just note this is the same as saying A squared plus B squared is congruent to 0 mod P. Okay, but now that's sort of not too bad because I know since P is congruent to 1 mod 4, there is a square root of -1 in FP. So -1 is a square in FP, which is the same as saying there is an A, there's an integer A, such that A squared is equal to -1 mod P. Okay, but then if I look at A squared plus 1 squared, so I can take sort of my B to be 1, I get 0 mod P, i.e. can take B to be equal to 1. So if I sort of use this value of A such that A squared is equal to -1 mod P, then I can just take my sort of value of B to be 1. And I get a solution to A squared plus B squared is equal to 0 mod P, or equivalently, sort of that says A squared plus B squared is a multiple of P. Okay, so that's not so bad. So the real trick of it then, and this is not so bad, at least sort of using this key fact that we've already established, that P is congruent to 1 mod 4, if and only if there's a square root of -1 in FP. Right, so once we have this, though, we need to do the second step. So we need to do this descent step, which says sort of if this multiple is really big, then we can sort of replace it with something smaller till we get down to P. So just for example, like where you might end up after this first step is you say you're trying to express 13 as a sum of 2 squares. Well, you might sort of just notice that 5 squared is congruent, says equal to -1 mod P. So if 5 squared is congruent to, or sorry, 5 squared is congruent to minus 1 mod 13. So 5 squared plus 1 squared is congruent to 0 mod 13. And if you really just compute it out, you have 5 squared plus 1 squared, that's 26, which is 2 times 13. So now your multiple is 2, but you want to express 13 as a sum of 2 squares, not 2 times 13. So you have to do something. You have to sort of change this guy so we can get a 1 here instead of a 2. So we have to somehow make this multiple smaller. Okay, and so that's what descent does. So what's the idea? So we have a squared plus b squared is equal to mp. What we want to do is you want to sort of factor out the m. But of course, you might not be able to do it, right? I mean, if m is not a square, you certainly won't be able to do it. If I want to factor out this 2, I'd have to divide 5 by the square root of 2 and 1 by the square root of 2. But then I wouldn't be left with integers. I'd have 5 over square root of 2 plus 1 over square root of 2 squared is equal to 13. So you can't quite do that because you need to stay in integers. But we can sort of be a little rougher. Instead of factoring out m, instead of factoring out the square root of m, I want to multiply by something. So I want to multiply a plus bi by a Gaussian integer. So using this thing that I know if I multiply it by a plus bi by a Gaussian integer, I'll get a new sum of 2 squares that adds up to the product of the norms, adds up to the product of the norms. So using this theorem we did earlier to get something where you can factor out m. So I'm going to temporarily, and the idea is I'm going to somehow temporarily make the problem worse. I'm going to multiply my a plus bi by something, so I'll get new numbers that square to something bigger than m times p, some larger multiple of m, or some larger multiple of p. But I'm going to do it in such a way that then I can then divide by m, and also get rid of, so if I divide a over m and b over m, then I'll get rid of an m squared on this side. And then once I've divided by that m, that m squared on this side, I'm actually going to end up with a smaller multiple of p. So I have to make it a little bit bigger so I can then divide to make it smaller like I actually want. And so for now, we're just going to treat it like a trick, but we'll explain on Thursday where this trick is coming from. I'm just going to tell you how to find the number to multiply it by. So we're going to we have this multiple m, and what we're going to do is we're going to take numbers u and v that are congruent to a and b modulo m. So modulo is multiple, not modulo p, but modulo m. And they're sitting in this range between, so they're u and v are, whoops. And I can take representatives in any range of length m. And so here the range I'm going to do is between minus m over 2, non-inclusive, up to m over 2 inclusive. I'm going to take, and the reason I want to take the representatives in this range is these are the representatives whose square will be the smallest. Okay, so I do that, and then if I make these choices, then u squared plus v squared is equal to m times r for some multiple r, and the reason is because, well, that's the same as saying u squared plus v squared is congruent to 0 mod m, but u squared plus v squared is equal to a squared plus b squared, which is definitely divisible by m. So a squared plus b squared is m times p, which is 0 mod, so it's 0 mod m. So because I chose u to be congruent to A and v to be congruent to B, this u squared plus v squared is the same as a squared plus b squared mod m. So it's 0 mod m. So u squared plus v squared is equal to m times r. Good. So this is equal to m times r. And then r is sort of just something else. And r is definitely not going to be p, or sort of not usually going to be p. Like r is just some other number. But the sort of r is going to be our new multiple, actually. So once we sort of make the manipulation. And so the key thing about r is that it's actually less than equal to m over 2. And that just follows from this equation. So u squared plus v squared is equal to m times r. On the other hand, like each of u squared and v squared is less than or equal to m squared over 4, just because I've taken u and v to be sort of between minus m over 2 and m over 2. So their squares are sort of between, are no bigger than the square of m over 2, which is m squared over 4. Okay. So, and then if I add m squared over 4 twice to itself, I get sort of just m over 2. So let me fix that. So I sort of, from this equation, I really get mr is less than equal to m squared over 2. And then I just divide by m. To deduce that r is less than equal to m over 2. So if I can sort of arrange using all this data to get something sort of such that a squared, sort of a prime squared plus b prime squared is r times p, then I'll sort of have succeeded. I mean, so I'll get some smaller multiple of p. Okay, and so that's what I do. And what did I say? I said I want to multiply by a Gaussian integer to get something sort of whose norm is bigger. And so which integer am I going to multiply? I'm going to multiply by u minus iv. Okay, so if I look at u minus iv times a plus ib, so this is giving me some new Gaussian integer. And if I take the norm of that, well, that's just the product of the two norms. Well, the norm of u minus iv is m times r. And the norm of a plus ib is m times p. So I get sort of two m's, which gives me an m squared. Then I get an r, so I have an r and a p. So the norm of this new Gaussian integer, I get by multiplying them together, is m squared times r times p. And that's the thing that's too big. And so that here I haven't helped myself. I've given myself a way to write a bigger thing as like a bigger multiple of p as a sum of two squares. But the point is, yeah, and so it's sort of be the square of this thing and this thing. If you expand it out, it gives you this. Let me write that out. So, I mean, what I have right now is au plus vb squared plus ub. Sorry, my u's and v's look similar. ub minus va squared, well, m squared r times p. So that's, again, so that's not helpful, except that now I'm actually able to divide this thing. These are actually both integers that are multiples of m. So I'm actually able to divide each of these by m, which is going to kill my m squared. So let me just sort of show you what that looks like real quick in this example for 13. So remember we had 5 squared plus 1 squared is 2 times 13. And so if I sort of set this up, well, m is 2. And so I'm looking for u and v between -1 and 1. And sort of u should be congruent to 5 and v should be congruent to 1. So and the option there is, it's not like u and v can only be 0 or 1 here. And so these are both odd. So u should be 1 and v should be 1. Whoops, and I did let me write this multiplication down right. So the multiplication is set up there. So I should do 1 minus I times 5 plus I. And that's equal to 4. So 5 times 1, oops, 6. 5 times 1 plus minus I times I. So minus I times I is minus I squared, which is 1. So I get 6, and then the multiple of I is minus 4i. Okay, and just as I said, sort of both these things are now divisible by 2, which was my m. So I sort of divide out, and I get I get 3 minus 2i. Okay, and it is the case. So there's some flexibility in what you multiply by. So that's why my example I changed that at some point in my notes. And so that's why my examples had the wrong thing here. The norm of 3 minus 2i is 3 squared plus 4 squared, which is 13. And that's what I wanted. I wanted 3 squared plus 2 squared, say, which is 13. And that's what I wanted. I wanted to get not 2 times 13, but just 13. And so I made the problem worse. Like, so if I squared 6 squared plus 4 squared, I get 52. Or sorry, if I do 6 squared, it's 36. Plus 4 squared is 16. So yeah, that gives me 52, which is 4 times 13. And so somehow that's worse. That's 4 times p. 13. That's 4 times p. But then because these 6 and 4 are both divisible with 2, it gets better once I divide by 2. Okay. So in general, why can you always divide these things by m? Well, yeah, so what I'm saying is I want to say a prime is equal to au minus bb over m, and b prime is ub plus ba over m. And what I've seen, from above, we get a prime squared plus b prime squared is equal to p, or r times p. But these are integers because au and minus bb and ub plus ba are both divisible by m. And so let's just check that. I mean, au minus bb, well, modulo m, u is congruent to a. Did I do this backwards? I'm going to pause it for a second and figure out what I did this backwards. Okay, sorry, I figured it out, and now I've unpaused it again. I had a minus sign in the wrong spot. So, so I was supposed to have au plus vb down here. So this was supposed to be coming from up here. And I was supposed to have ub minus va down here. So let me just fix that. So this one's a plus and this one's a minus. Okay, now if I continue what I was doing, so I have au plus vb. This is equal to a times a plus v times v mod m, which is a squared plus b squared mod m. But a squared plus b squared is divisible by 0. Or sorry, a squared plus b squared is divisible by m, so this is just 0. So the reason I got a times a plus b times b is just because u is by choice congruent to a mod m, and v is I chose to be congruent to b mod m. So this is 0 mod m, i.e. m divides au plus bb. So a prime is an integer. Similarly, if I do so I'm having trouble moving this. If I do ub minus va, I want to show that's divisible by m. Well, that's congruent to u is so ab minus ba, which is congruent to 0 mod m. I mean, ab is ba. Again, just because u is congruent to a and v is congruent to b mod m. So m divides ub minus va. And thus b prime, which is ub minus va over m, really is an integer. Okay, so I got these new integers a prime and b prime such that a prime squared plus b prime squared is r times p. And just remember, r was less than or equal to m over 2. So really this gave me what I want. Some integers such that the sum of their squares gives me some smaller multiple of p. And right then, to get down to p, sort of if this new multiple is not 1, you just sort of repeat the whole process, and then you get some smaller multiple again, and until sort of you land at p. Okay. And so since you're cutting down, I mean, sort of it's even stronger than sort of doing something smaller. Like each time you sort of cut down this multiple, sorry, where was this estimate? Yeah, each time you cut down this multiple by sort of at least a half, you sort of cut it in two. So actually sort of, I mean, you get rid of this multiple quite quick in practice by doing this procedure. Okay, so let's do just an example of carrying this out. So I have 9 squared plus 7 squared. That's 81 plus 49. If I add those together, I get 130, which is 10 times 13. And so I can use this to express 13 as a sum of 2 squares. Of course, I mean, we already know how to express 13 as 2 squared plus 3 squared, but I just want to show you how sort of this descent process here would recover this. Starting, like say you didn't know that, starting from just, you knew you could get some multiple of 13. Okay, well, so m is 10. So we're going to do m over 2 is 5. So we're looking at for sort of u and v between -5 and 5. And just recall a is 9 and b is 7. P is 13, I guess. So that's sort of the setup. And so u is supposed to be between -5 and 5 and congruent to a mod 10, so mod m. So that means we should take u, so u congruent to a mod. So a is 9. And so between in that range, that means we have to take u to be -1. And then sort of, since v is going to 7 mod 10, and again, sort of you're in the range between -5 and 5, you have to take v to be -3. Okay, and then I just look at sort of u minus vi times a plus bi. So this gives me -1 plus 3i times 9 plus 7i. Okay, and then I just expand that out. So I get -9 minus 21. So I get, sorry, that's not right, -9. Yeah, so yeah, good. I get -9 minus 21. So I get -30 plus the multiple of I. So the multiple of I is 27i minus 7i, so plus 20i. Okay, good. And now if I sort of add these two squares, I'm going to get sort of some really big multiple of 13. But the point is, again, now I can divide by m. So I can divide by 10. And I get sort of -3 plus 2i. And now I just check. So -3 squared plus 2 squared, that's just 13. So actually I'm done. If I got sort of, what I knew was going to happen for sure is that even if I didn't get 13, I would get some smaller multiple than 13. In fact, I would get sort of a multiple less than 10 over 2. So I get sort of a multiple sort of at most 5 times 13. And then I would have to repeat this process again if I sort of didn't get the multiple 1. But here I sort of just got the multiple 1, so I'm actually done. Okay, so that's how you can use this algorithm in practice. Sort of if you start with a sum of 2 squares that gives you some multiple. On the exercise, on the worksheet, we'll talk a little bit about how you can sort of find sort of one of these first ones in practice as well. To start with, good, but it's okay. So we've sort of established this theorem sort of by giving this algorithm. So we know if p is prime, then p is if P is a prime congruent to 1 mod 4, then you can write it as a squared plus B squared. And sort of now we know how to do it. Sort of if you're given sort of some formula, a squared plus B squared is some multiple of P by this descent method. So that's all I wanted to cover today. And then, well, this descent method probably looks pretty familiar to kinds of things we did before. And it's no surprise because actually this descent method is just the Euclidean algorithm, but sort of instead of in Z brackets I. So I'm going to explain that on Thursday, and then we'll use that to understand sort of what unique factorization looks like in Z brackets I, and to understand exactly, and then using that we'll understand exactly not just for which primes are sums of two squares, but actually all n are sums of two squares. So now sort of we know so far as like any prime that's congruent, so any number that's a product of primes congruent to 1 mod 4 or 2 is the sum of two squares, just by combining sort of this theorem with sort of this multiplication theorem. But in like there are other numbers that are not like sort of like 3 squared is a sum of two squares. It's 3 squared plus 0 squared, and sort of 3 is not congruent to 1 mod 4. But in fact, that turns out to be essentially like the only other thing that can happen. And we'll explain that using unique factorization in the Gaussian integers on Thursday. So I'll see you in class on Tuesday. Thanks.